Hey, Coffee Compiler Club. Short notice, weird time today, so I don't know who else shows up. Gonna talk compilers, language runtimes, and yet another way in which the heat failed in my house. This is all very exciting, or not. That's it. I recorded. Everyone knows the spiel. We're alive. We're recorded. Fine. Um, I had a busy week. I did a modest amount of coding, and I did a whole lot of rescuing various sudden failures in my house. I have more failures to go. Fine. That's it. Anyone want to say anything before I, give it up and say, why are we here? See, oh, here's my download next fails from, yeah, I get a slew. Every attempt to go send a mail out in about 5, 10 minutes gives me a slew of, we can't send your mail and we're not going to tell you why. Well, we're refusing if we can totally send it. We're refusing to send your mail. So, there you go. What you gonna do about it? Um, what can I say here? I've been doing hashgraph all week when I'm coding and doing doctor's appointments and failures in heating when I'm not. And that's it. No news is good news. Or not. Hang on. Um, what were you talking about earlier, Matt? Oh, I talked to Jack Chiquette at NVIDIA doing the, next generation of whatever, GPUs with tiling and warping and stuff. Here's Apo, who is going to say something too. Apo, you on? You're looking like your video and muted. And maybe I was going to talk you into talking about what you were doing with JavaScript. Oh no, lifetime of why is Rust borrow checker lifetime things contravariant? That I read your thing and I didn't get it, and I would love to have more explanation.
Sorry, I have my headphones muted for a moment there, but I got the rest. You want me to talk about that? I can talk about
I
that.
would, yeah, I'd love it.
So this is like crackpot level theory type of thing, but it's somewhat based on actual facts of the matter. So everybody on the internet knows that Rust cannot represent self-referential structs, right? You
Okay,
can't
yeah.
use the lifetimes for that because that's just not what they're for. Um, and
Which, by the way,
I've
sucks
been
for Sea of Nodes compilers. Several people have tried
yeah
this because
yeah
immediately you can't have cycles in your graph.
yeah
Yeah,
and so I'm building a JavaScript engine which of course has cycles within the heap.
yeah.
Um, and I'm still using the same type, same handle type that I give out to users or to the stack inside the heap. So it has a lifetime. But these are unrooted handles, i.e., there's like if you forget to use it properly, it is unsafe, and I'm just going to panic the engine at that point. Um,
Oh, this is where you were
so
talking about having annotations everywhere.
yeah, yeah.
Okay.
So the like the unbind bind, the annotation stuff, that is about the user on the stack making sure that they're not accidentally forgetting to root their handle when they should be rooting it. Um, and the so on the heap, the lifetime is then static because that's the like only reasonable lifetime there. But then whenever let's say I have a user who wants to give me a value to write onto the heap, like for instance, they're doing a set operation, like set value on a JavaScript object. That's a write of a handle from the stack to the heap. Now they have a temporary lifetime, a short lifetime, and I want to write it into the heap where it has a static lifetime. That doesn't work. That would be if that worked, it would be totally violating the Rust borrow
Right,
checker principles.
you're cheatily increasing the lifetime of the handler
Yeah,
thing.
yeah.
Right.
And I've been doing this for like a year and a half at this point, and suddenly, like last Sunday, I realized, wait, this this actually works if the lifetime reference or if the lifetime isn't covariant, but it's contravariant. Um,
That's usually in
i.e.
reference
that
to functions.
yeah, so you can't generally, I guess, you can't think of lifetimes as types, but they do have a variance. And for a function that takes a
Why can't you
reference,
think of them as types?
um, they don't have like yeah. It's better to not think about
It's
that, I
not
guess. But
one of the usual interpretations of types is a collection of values, a set, literally a
yeah,
set. And then you set intersection and set union to describe type operations. And now
yeah,
I
I
don't
guess
make, I see there's no set like, I don't have a mindset for set like things on lifetimes.
they're actually behind the scenes. There kind of is, especially with the coming, hopefully coming Polonius borrow checker. It actually deals with lifetimes as a set of places where the lifetime is valid, or a set
Okay.
of points.
Yeah,
So
right.
then I guess it maybe makes sense. But anyway, so I started looking into this, like what if I turn the handles from being covariant on the lifetime to being contravariant? And the answer kind of is that like a lot of things just become very nice. The heap has a static lifetime, which means that taking a handle from the heap and putting it on the stack is something that cannot be done without a manual lifetime cast, because contravariance means you can't go from a larger lifetime to a shorter lifetime directly. And that's kind of how it should be. Like these are unrooted handles, so taking it from the safe place and putting it onto the unsafe place, that should be unsafe, right?
Well, that's what I'm
And
trying to figure out. You're moving the handle. So the object's lifetime's
oh,
pinned by the heap, so it lives on forever. So the
yeah,
guy that went on
but
the stack should be okay forever. That's what
the
I'm missing.
the the because it's an unrooted handle, the object on the heap might still be there, but it might get moved around whenever garbage collection happens.
Okay.
And the handle doesn't magically change to point to the new place.
Uh,
So that's the unsafety of an unrooted handle. It doesn't follow wherever the object moves. And also, it doesn't keep the object from being garbage collected
yeah.
either.
Right. Okay. Okay. So the cast actually increases the lifetime counter on the object somehow. I mean, it makes it more alive. You get two pointers to it, one in the stack and one in the heap.
Mm, well, it's not reference counting, so it doesn't.
I understand it's not reference counting,
Yeah,
but you end up with two pointers to it. Something on
yeah,
this.
yeah. You make a copy of the reference. In my cases, they're not actually pointers, but just indexes. But it's the same
Yeah.
thing at the end of the day. Yeah. Um, and another thing, or like, so this is the kind of unsafe direction, moving from the heap to the stack. But the other direction, if you have a handle on the stack, at least, and that you believe is safe, you've done your due diligence, it's all
I made a
proper,
mistake there.
and then you put it onto the heap. That's like obviously safe. Like, of course, you can
Yeah.
give your handle and write it onto the heap like that. It just makes sense. The lifetimes suddenly work very nicely. Um, the unfortunate thing is that there is still no like this doesn't magically give you lifetime safety because unrooted handles are just fundamentally not safe. There's kind of they are very dangerous. So you still need to do your due diligence. But it I'm kind of I haven't really looked into this yet, but I have a feeling that there are some things some parts about self-referential structs where contravariant lifetimes actually make things quite a bit nicer. Though it's this is like crackpot level theory, so it might be that I end up being just wrong.
Well, I don't have an answer here, and it's one of the things I want to go find my time to go explore. But I can't say left or right, up or down on it.
Yeah. That was it so that Mojo also has a concept of lifetimes.
It totally does, and it might be that it's contrarian as well. This should be in the online documentation for it. There is definitely some rules about how they try to do the management there. The other
Yeah.
thing they have is an origin, which basically a separate address space. So I have a GPU space versus a heap space. But you can have different caching layers where you allocate different spaces. Both of those, lifetime and space they belong in my head, fall into some sort of lifetime management. And yeah, you would like to have something that says I've counted it carefully and I'm not moving you from a GPU memory to a CPU memory for free. You had to take the primitive to go move that data or
Yeah.
whatever. From this
Yeah.
layer of special magic memory in a GPU to that layer of special magic memory in a GPU. Um,
That memory, like tracking which memory it is in,
yeah,
that
right.
kind of sounds like branding. So in Rust, if you make an invariant lifetime which cannot grow or shrink,
Mm,
and then you make sure that it can only exist or that it cannot be unified with any
okay.
other lifetime, then you get a unique brand that you can kind of pass through your whole call chain, and
Mm.
you are guaranteed that it will never ever mix up with something
Mixed
else.
with something else. That's interesting. Yeah, that's the kind of thing they're dealing with. Yeah, the motion between CPU memory, GPUs, different memories are all carefully tracked. And there's a lot of magic in there that I think is, I want to say is very ad hoc. Maybe that's the right word for it. So they have
It
a
seems like
nice
the
goal, but I'm not certain they have a a good theory to make it simple, right?
hmm,
So maybe there isn't one, and maybe there is, and I've missed it, or maybe maybe they're still
yeah.
looking, and maybe Rust is still looking. I heard you just say they have a new borrow checker coming up, who's going to change how they do valid ranges, I assume.
It's been in the works for at least 6 or 7 years now. It's coming
Six
any
or
day.
7 years.
Yeah. I
Wow.
think they're now at like parity, and now the problem is getting the performance up to snuff because it's like something like 1,000 times or 3,000 times slower. Um, which I hearing that sounds horrible, but then on the other hand, like the actual compile times of Rust for the borrow checker isn't really the problem. So I'm not.
I
I
see.
guess it is. 3,000 is probably enough to make it a problem, but yeah,
Right. I gotcha. Maybe you don't care. And at that level of numbers, it's almost surely like there's an asymptotic, like it's an algorithm change. Somebody will
yeah,
change the
yeah.
algorithm and then they'll drop the orders of magnitude off and it'll be fine, is my guess. But they must have changed some kind of serious algorithm. I have
Yes.
no idea. See, I still want to play in this space. This is like this kind of algorithm hacking is like things I'm good at and I have not played here. Definitely
Uh,
want to screw around.
the GPU memory stuff as well. I actually ended up reading. There was a discussion about this around Rust fairly recently that I ended up reading, where it really seems like not even the compilers really have a really good handle on this whole like how CPU and GPU memory should be shared and not shared. Because like LLVM, for instance, has this system of address spaces for pointers
In the compiler. Yeah, in
in the
times
compiler.
past,
Yeah,
in C++, you just brought along an allocation manager, but it's totally on the programmer to not mix and match between
yeah,
memories from different allocation managers.
yeah. So the LLVM has this concept, but it's not really exposed all that much. C C has some way to define that
C, the language?
apparently. Yeah, or is it the C OpenCL, maybe the
Oh,
variant of C?
OpenCL would be very, very different than C.
Yeah.
Um,
Um,
OpenCL would make more sense too, but I have no idea. Like C, the language,
yeah.
as far as I know, has no special concept of address space ranges.
I
Many
think
HPC computing languages do, like Chapel for
hmm,
whatever, the Fortran replacement worked on by guys deal forever.
uh,
Things like that totally have address space shenanigans they want to play with.
yeah. But
But I
then
don't know.
apparently like GCC, for instance, has very different ideas of how this works and so on. So
Eh.
it seems to be a bit of a mixed bag, even in the mainstream compilers world.
Yeah, it could be because like I said, I'm not in a mainstream language. I don't remember anyone doing it directly in a bunch of different, one-offs for, well, HPC, here you go. I know that people tried different things. MPI. Um, Gosh, yeah, I don't know. And then Rust playing games with borrow checkers headed down that way. Be nice if there was some good theory here.
Um,
It's just like
See
it
where
just
it
reeks
goes.
of good type theory, and without having me play with it, I can't say that there's actually any theory there that makes sense. But it reeks like it ought to have a theory.
Just needs time and work, and nobody got time or the will to work, I guess.
Yes, well, I have the will, but not the time. Hashgraph seems very straightforward and has nothing to do with nothing, but they'll pay money, and there's a need for it somewhere in the universe. Conceptually, there is a need to say something about two different people come to an agreement or whatever. Mutually distrusting parties can all agree on something more complicated than just, I sold this to you or whatever. I moved ownership around. There's something more complicated you want to do there. And how can we make that happen? And that's hashgraph. Okay, fine. Um, like I said, it's all straightforward. It's a giant piggledy pile of random stuff that they inherited from the Ethereum open source stuff, plus some amount of their add-ons and a hardcore theory. Go find Adrian. Hey, Adrian. Hardcore theory of how to do efficiently the Byzantine, like a strong Byzantine uh, um, correlations or whatever. Everyone comes to an agreement. This is like whenever you play online shooter video games, there's a large contingent of hackers cheating. It's very obvious, right? And surely there's a way to pull out this Byzantine theory amongst the different CPUs that are playing in a cooperative game that we come to trust that says that you didn't actually play cheaty games. And so whether or not gaming is the right drive or right motivation, there's clearly a need to have mutually agreed upon trust from untrustworthy parties, untrusting parties. So they've added that, and then they've added some interesting hacks to the underlying mechanism for different kinds of transactions. But mostly the actual engine for doing the smart contracts was whatever they got out of Ethereum with very minor hacks. And that was all designed by, I don't know, young kids, like 19-year-olds, not to do anything with performant computing. And they made sort of a series of systemic classic mistakes that make it really bad or really tough to get high performance out for no good reason. Like, because this just didn't know better. And the thing has like no pointers, no structures, no arrays per se, except you get a flat virtual memory space you can deal with. Um, it's WASM minus minus, if you will. And then there's some plus hooks for doing things with crypto hashes and stuff that, make sense in their specific domain, but the actual coding engine, WASM minus minus. And now go read market data and compute a 30-day rolling average and use that to drive whether or not you're going to triage or arbitrage some particular coin or whatever you're going to do. Fucking nightmare to go load in, external data and do some stupid math calculation that all parties can agree that because the rolling average hit X, this happened. No, you can't. It's like a nightmare to write this code. So that's where I'm at. it's a relatively easy pickings in the sense that the bar is very low here. I'm stepping over a low bar. Maybe we'll get it somewhat better down the road than the current state of affairs. Mm-mm. Today's mystery was turned out that I didn't have my 256-bit math overflow carry operation bit twiddly done. This is like a deep dive into Hacker's Delight and go find the stupid page where it says, oh, this, and you do X XOR, Y XOR, sum, twiddle, not, and, or, boom, done. Okay, didn't get it right. I got to sort it out, and I got it right now, I believe. But that's the kind of thing that is like this, or whatever. It's all like nonsense, low level, mindless stuff you have to pound through. The actual
I,
interpreter is just a first cut
mm,
dumbass thing, but without miles of allocation. The drowning in allocation is what the old one
ooh.
does. So the new one is a lot less allocation. Oh my God, a lot less. We'll see.
I I actually after playing around with HTML and CSS for about a month, having a lot of fun, had a lot of fun with that. But finally, yesterday, I got back to what I was supposed to be doing for the past month,
Right.
which is optimizing a particular data flow graph and kind of getting back into the code, looking into like what
Right.
was I doing, and okay, let's get this like simplest thing working, and okay, now it works. So now this is supposed to be faster than the previous one, which was drowning in allocations.
Right.
Um,
Yes.
and like horrible allocations. I just I gotta give it to myself. Uh, 3 to 4 year back, 3 or 4 years back, I rewrote these nodes in this graph from being they were okay but not great. I wrote them to be in some ways better, but like 100 bytes per node,
Mm-hmm. Mm-hmm.
which is like ridiculous.
Notes
Um,
for an IR or notes.
it's yeah, it's basically an IR. It's
Okay.
a take essentially a JavaScript based DSL, turn it into a data flow graph that whenever an update happens, it just
Right.
paints the whole update tree
Yep.
and runs the code. Um, but yeah, I have already turned it into like a nice flat memory space with like 4 allocations in total, and it's gone down from being 100 bytes per node to on average like 7 bytes. That's
Yeah. Okay. Yeah.
that's what it took.
Uh-huh.
And then I spin it up on a test page just to see like so how did this actually perform? And creating the page is really good. And then it starts getting to actually running the graph, and it's taking like 4 to 5 times the time it took previously,
Uh-huh.
actually more than that. And I look at what is it doing. One of the things I had dropped out was some redundant information that turns out isn't actually redundant, and I had a little algorithm to calculate it by doing an index of from the beginning of the memory space, finding
Yeah. Yeah.
where am I, and then
Yes. It's
based on
like
that,
quadratic
figuring,
just right away.
yeah, yeah. So it's doing that, and nearly every single operation is just starting from the beginning, figuring out where am
Yes.
I. Yeah, that was.
And you fix that.
I haven't yet fixed that.
Oh
But I
no, because I want
think
to hear the number after you
that
fix it. It's like compilers are always full of quadratic worse algorithms that accidentally get introduced that you have no intent and can easily fix. You just have to go fucking profile and try something for a while, and you're like, oh, wait a second.
yeah.
Something stupid happened here. Oh, I need to keep this stupid bit around so I can avoid this n squared lookup every time. Uh-huh.
Yeah, that's the annoying part. Like now, what do I keep and where do I put it? Because
Just go up from
most
7 to 8.
yeah,
I mean, the
I
drop from 100 to 7 is pretty good. Maybe go to
it
a drop
is.
from 100 to 10, and kept some of the caching around.
I probably need to add like 4 bits. Sorry, 4 bytes.
4 bytes. Okay.
For
Yeah, like
the
simple is really bulky compared to C2. although I know exactly where the bulk is. And it's, I have a node which has a pointer to an array list, which has a pointer to an array plus the length. And all things are pointer sized and they could all be index sized and the array could be inline in the node. And if you started doing all these things, I could cut my nodes from 100 odd bytes to, and not seven, but I could probably get them under 16. And I could handle variant size nodes more efficiently by doing a flat layout of memory and have two adjacent slots being for a fat guy or whatever. And that's pending as this would be a cool hack somebody could go do. And we know that there's going to be like a 10x speed up, hanging around in there somewhere. There's a big speed up waiting to happen. I don't have big enough test cases to matter yet, but it'll happen.
Yeah. This for my case, the test page I was using came from a an internal customer who had created for me a page with 1,000 components that then generates a graph that is around 700,000 nodes. So
Yeah, okay, right. Yeah, yeah,
um,
yeah. It's big
we
enough
get
to care.
something out of that. Yeah.
Yeah, yeah. All right, now I gotta go find Ryan here. Hey, Ryan. There we go.
Greetings. Can you
We're
hear me?
talking. Yes, we can hear you. We're talking compiler, the life of the compiler writer and implementation details that reach out to bite you in the butt.
Oh,
It's
so I like my design.
there
I
you
feel
go.
like it's it's very extendable. Although I had to because of C++ isms, I found I had to rewrite it to make it
Everybody
compile
likes their own
faster.
design 100%. And then, they look at somebody else's design and say, I can see all the bad parts. And then they look at their own and like, actually, this kind of sucks over here too, but I don't want to do the work to go do anything about it. So there you
See,
go. And then on
m
the next go around, the next new compiler, you go and deal with the horrible things, and they're like, this new thing is really cool. It fixes all the bad things. And I brought in a bunch of bad things that I avoided in the prior one, and I don't know. There's a coming around and goes around. Try a few more compiler implementations before you say that I found the best one.
well, I would say that it's a good way to make it easy to write the compiler. I don't know. I'll have to figure out what the performance is like later when I kind of get it working, you
Oh,
know.
that is not even where I'm going at here. I'm like, the ease of implementing it really until you try a couple different compilers, like not even two or three, but several, and live with them as they get big and become like corporate managed and whatever. It's hard to say what is or is not long-term viable. I mean, I knew my first compiler hands down. I wrote it myself. I knew the second compiler I went in a big company with, hands down. It was big, nasty, complicated. Okay, but it was new, so it was my head wasn't full of shit, and so I picked it all up and I ran with it. But later I could look back and say that's kind of like really grotesquely overhead. Then there was another compiler, and a lot of the grotesque overheads were common between many of them. And somewhere in that period of my life, I ran after the simpler IR, and then I did a bunch of variations on the sea of nodes, and ended up where I'm at now. But I'm claiming there was a lot of well, school of hard knocks, and I always loved whatever I had at the time I had it, and then later I'd be looking back going twitchy.
Yeah, I haven't gotten that far because like in mine I've just been working on like, hey, here's the front end LLVM, go do all the rest of the work. That's kind of my
You,
strategy.
you
So,
maybe if you feed into somebody else, like you cut off at a certain point, you're going to have different decisions to be made. That's for sure. You decide I'm not doing this piece over there, you walk away from it.
well, I'll probably at some point get into like doing the code gen or optimizations, especially if I want to like self-host the compiler in its own language, you know?
Yeah.
Um, because like LLVM is in C++, plus plus, but at least for the early implementations, um, you
You
know,
remember the fellow was on a couple weeks ago. He did his own C compiler from scratch, all the way through. He went through like four different IRs at different points. And it's because he had different goals and he wrote them at different points in time. And then he admitted he had, annoying translation issues going on, but he didn't want to have the time and energy to go rebuild. And I totally get that. One of the things I've done with Simple is I can go all the way to the back end and out without having to rebuild the IR, but I don't know. That's certainly not how I started in life, and I don't know that's a necessary goal, but it seems like it's a good thing.
I feel like I've created an AR that is like general enough that I could create optimization passes over it if I wanted to. Like I
Yeah,
probably won't in the initial versions. Like the initial version is just going to be turn this IR into LLVM IR and then run the LLVM optimizations. But it's
yeah, yeah, right.
like
I get
the
it.
it's like load and store and stuff like that. So it's like this could definitely be optimized by itself at some point.
So like the things that I've seen that make a difference in how your IR is structured, it's what do you do about function calls is one of them. What do you do when it comes time to do scheduling? If you've already bought into basic blocks, that's sort of straightforward. And if you haven't, then you have all kinds of decisions you have to deal with. Um, what do you do about changing the base IR in bulk because you're switching from front end stuff to machine code, or you're doing tiered versions of I have matrix multiplies as a primitive, and then I want to expand it later as code. I have x86 outputs or I don't, kind of thing. And then there's a final back-end bits, like what I do about generating bits. I'm going to print out assembly and call gas. Or am I going to put bits out? So these kind of these things mess with your IR design decisions.
Yeah, I did see like where I need to like put, at some point like source locations in the IR
Oh,
and
debug
then
info.
yeah.
Oh, debug info never messed with me, but I had to carry it through, so it extended the IR, yes, but it didn't change the structure of the IR. If that makes sense.
Yeah, mine's like let's see what I have. I have like, int add, int sub, mod, div
Right.
compares, pointer compares, global
So you have a
compares,
series, you have an
bitwise.
ops. Somebody has a list of ops, so that's only a piece of the IR. Then there's one op is related to another. Where do the inputs and outputs come and go? So SSA points, or you're in an AST or whatever. And then I went from an idealized integer add to an x86 add from memory. And then I have these adds and subtracts and multiplies and divides, but I want to reschedule them and have some sort of basic block layout or then global layout and then loop
Oh yeah.
analysis, shit like
Yeah,
that.
I didn't do any of that. Like it's like, okay,
Right. No, no,
here's
no, no problem.
slots.
That's what I'm just saying is that picking the ops is just one piece of the puzzle, and there are a bunch of other pieces that you have to pick. You'll be forced to pick, especially if you try to go past LLVM. But even where you're at, you should have edges now. What do you do for your edges?
Well, there's branch and there's jump, and
Okay,
that's
that's control flow graph edges. What do you do about data flow edges? You have an add, but an add of what? An add of some input over there and some input over there. How do
yeah.
you
Yeah,
represent them?
so it's just an output to another like a local. You add to take two inputs from two locals and
Okay.
stick the result in another local.
So when you have an add and has inputs from two locals and goes to an output, are they statically single assigned?
No.
Okay, so it's
That
not, yeah, no,
happens.
no, but it makes a difference, right? So then you don't have fee functions, but you don't have the SSA goodness. Whether or not your add inputs are pointers or indices are kind of little this, little that. I've gone both ways and I'll go both ways again. Kind of depends on where I'm at. But
Yeah,
you need to have a list of them. But the SSA or not, I guess, is the big that messes with your IR.
definitely. Yeah, I've thought about it. But it's so much easier to implement if you don't do SSA. And so LLVM is
It's
very
so
good,
much harder to
honestly.
optimize if you don't do SSA. That's the trick with SSA. It's all about fast, cool, clean, easy optimizations.
And I found that LLVM is smart enough to just if optimize it all away, it doesn't matter.
Right. No, no. You're a friend in LLVM, then you don't have this question. And now you don't actually kind of need a DAG, a graph. You could get away with an AST.
Because like with you can still kind of get the SSA thing, right? Which is where you just say, okay, the SSA is like I load from my Aloka and then do something with it and then store. And then LLVM will like hoist those Alokas and be like, okay, there's this mem to rig task, right? It's like, okay, these
You're
actually
no, there's a substantial difference. There's my okay. Pharmacy's right now. Yet another trip out of town, unrelated to anything else. Okay. Yeah, no, SSA is it is a major difference in how you set up the IR in exchange for a major difference in how you do optimizations. But if your optimizations are done by LLVM, you don't care.
Right, but there's the mem to reg pass, which means basically it'll convert
Yeah, right.
like
I'm
the
saying
local based address thing. Like all you SSA the addresses, right? And then you
yes.
just load and store from the addresses. And then the
I
mem to reg pass will say, hey, these actually don't need to be address loads and stores. They could just be SSA variables the whole time.
right.
And it's very good at that. And that's actually what Clang and GCC
That
were.
comes
So
out of any of the more reasonable SSA transforms. So I get that behavior in simple and in C2 straight from reading the bytecodes straight into IR. And I'm doing all those optimizations, but I don't do anything. How do I say this correctly? I don't have to do anything like a separate pass. Literally the parsing of the text gives me the preloaded mem to reg, post mem to reg already. It's done in one, not just one pass, one tiny paragraph of code that says, "Oh, this is the local variable." Boom, done. I mean, I've given it to you with all the SSA goodness and the memory SSA goodness all done. There's nothing to it. And this is the sort of the magic of SSA.
yeah,
I
SSA
play with
is
SSA at
I
some
think it's
future date.
nice for doing the optimizations because it like lets you reason about okay where all the data came from and then like okay you can
Yeah, I encourage you to try optimizations with and without SSA at some future date and see what you think. The stuff you talked about, LLVM did a mem to reg pass. Yeah, I got that already, even going into SSA form because the act of going into SSA form get me
yeah
90% of
I
SSA.
could do some of that because like my the IR that I have like operations like consume their inputs and
Yeah,
like you can say, okay, if this was produced by like if we have a load somewhere and then we do some operations that consume the inputs, because like there's two sort of paths that like an operation could take. Like one is you could use it like in a consume operation, which can be treated like SSA, or you could do like make ref to the local,
I'm
which
encour the reason I'm encouraging SSA is because once you flip to everything as SSA, your mindset, how you view the problem changes. And a lot of the distinctions you're drawing between it's in memory or it's not, or it's consumed or it's not, they just go away. And you can quit worrying about them. That is part of the mindset change that comes with SSA. The complete SSA thing, not I have Z's.
well like I'm looking at this like okay if I have a local right and I only use the local as so like um if the local is like produced by an instruction like an add instruction and then it's consumed by another instruction that could be like just feed forward through SSA when I generate the SSA form right because I have to generate
Right.
SSA
Yes.
when I'm generating
Yes.
LLVM. But if I do like, okay, instead of just feeding it forward, I am like there's the like make pointer to or make reference instruction. Then I'm like, okay, I actually, if I want to call make ref, then this local needs to actually like have stack space allocated for it, right? And then it needs an alloca. So like I can scan what instructions are called on the local, and then based on that, I can know whether it can be SSA or not.
No, I think
I mean,
I
like
think
whether sorry, not SSA, but like whether or not it
okay.
can be like directly allocated as like an SSA
Yes.
int, or whether it's like stored in the unalloca or not stored. So like,
Yeah. Right. I think you're getting closer. I think you need to play with sort of a serious SSA implementation where everything's SSA and not, and like these distinctions start to like fade out. So I'm not doing C. You can't take an address of a stack variable in whatever languages I'm doing, which is fine. I can certainly make an object and put things in it, take things out. And if I put things in and take them out, the things that go in and out, they're still SSA form on memory as well as SSA form on registers without any distinction on my part of whether it's memory or not the memory in terms of how I
that's
treat
true.
it. It's just another
Yeah,
node in the graph, another edge in the graph. Happens to be memory labeled instead of not memory labeled, but it didn't really matter. The lifting from it was a junk load and store in and out of a struct, like a stack, like I make a bogus stack frame, an alloc stack frame. And I store something in and load it out, and it was useless, and I could have just kept it out. That's all done with like little people's. mindless short pieces of code, like 2 lines of code that pull something out. I store it, I load it back to back. The load operation looks for a prior store and says, nah, this wasn't necessary. I didn't have to think about it. That was the thing that kind of got me with SSA. Once I got to that point where there's SSA everywhere, including on the memory cells, you don't have to think about it anymore. It just works. And that's what I'm encouraging you to go play the game and look at it from another direction. It's like functional programming versus imperative programming.
Yeah, I've got too
Never done one or
much.
the other. It's hard to tell. When you've done them both, you can see places where, oh yeah, these other guys have a real, there's something real there.
I've got too much work on the front end to do before I start working in the
Yeah,
middle
fine.
because like my language is based on C++, so like overloading and templates and like this is a lot of front end
No, the front end, yeah,
work,
yeah, right. There's no
code
question.
gen.
I mean, I
I
have too
I
much work
I
to do
I
too.
am not ready to like be like, oh, all this stuff that LLVM is doing for me, let me do that again, even though I haven't finished the front end like code gen. Like I don't have inheritance, I don't have a whole bunch of stuff
Right.
working.
Yeah, so no worries about being defensive. Simple doesn't have a bunch of things I want to have in it, and I don't have time for them either.
I'll
Someday
do it
down the
eventually.
road, right,
Yeah.
someday down the road, I think it'll help. There's certainly doing a whole lot of functional programming opened my mind to another way to view a whole lot of problems. And that was very helpful. And the same kind of guess salt leap happened with SSA. Once I embraced it fully, it made a big change in how I think about a lot of problems.
Yeah,
Of course.
I have a sort of a good experience with the sort of semi-pure functional programming. I like it, but I also like I have like this kind of value-oriented programming model, which is like, okay, I can make something that's like imperatively structured, but it's pure in the sense that it takes its, the input functional parameters and it transforms them and then it returns a value and it doesn't have side effects elsewhere in the program, right? Like it's not
Hmm.
mutating things, it's just taking the inputs, imperatively mutating them somehow, and
Hmm.
then returning the output. And then that's kind of how I like to structure most of my code. And I find that it's reasonably fast and also easy to reason about.
Yeah, easy to reason about. It's a big one. You get the problem solved and you can move on to other things. All right. What else? You can be short today.
I have I got my scheduler working and it can even run in a loop continuously with thread sanitizer and not have any problems.
Okay.
Multi-threaded. Created not only does it work, but I have the sharded map. It was a 50 times performance improvement versus the standard map in mutex. Part of
Oh,
that's
and
because
mutex. Yes. Yeah. Okay.
yeah,
So
I
sharded
had
map. Yeah.
yeah, it's an unordered sharded map. So I went from standard map, which is um not, there's one mutex, right? And
Hmm.
then it's a ordered map, and then I went to unordered map, and then I split it into like 16 shards on this PC because it's
Right.
like based on however many cores you have,
Right.
pretty much. So
Right.
if you have a 96 core Threadripper, then it's gonna create like, well,
Right.
96.
This is what concurrent hash map does for Java. Adds a
Yeah,
bunch of slices or whatever shards and locks per shard. And it only has to lock when you do writes. Don't have to lock on reads. That's a good one.
yeah.
And
So
non-blocking hash map was faster than concurrent hash map in basically every case because there's never a lock taken under any circumstance. That
yeah,
helps.
I could share my screen, show some of the test problems. It's not that different from last time, except this time it's working. Um,
A little bit. Let's see here. I don't want to go forever here. Hang on, hang on. Yep, do it.
okay. Allow over and okay. So like I can run this, and this is now 100% reliable and very threaded. So like, um, so I had to create a new little data structure, little starting map, but like, let me show the main function
So,
here.
so talk about what problem you're trying to solve.
So this is still the library implementation. This is like
Library implementation for what?
the query graph, which is like the fork join kind of thing,
Okay.
scheduler.
So you have a
Um,
fork join, and you're trying to yeah, which is fine, and
right.
you're
So
trying to
like
do
I
something.
have
You have sum over an array, a length of whatever large array, sum over the elements in a large array.
so like Fibonacci query. So you create queries, right? And then the queries can be whatever you want. And so like I'll go to query, it's got an input type, an output type. Um, and then you have like when you create your graph, you register the handlers for each query type with the specification for the query handler, which is like, okay, here's the query it's handling, and then here's a list of the queries that it depends on. And then you have your implementation coroutine. So it's like a coroutine thing. So um, like if I go to range sum, it's gonna yield multiple dependencies on other queries, and then it's gonna wait on them. So you create the queries, the query request, you can yield them as a dependency, and then you can co-await them. Or you could just co-await them right away, but then you don't get parallelism. So if for the parallelism, you have to yield the dependencies before you like await them, because like the await will schedule them, but if you await one that's not scheduled, then you'll
Oh, I
create
see.
there would be no like fan out. So to get the fan
Okay.
out, you first yield them as a
Yeah.
dependency. You could actually technically only this one is needed. Like this one here doesn't really do anything because it's going to await it first.
Yes, I
Um,
understand. Basically saying every time they don't start the launching in parallel until I do the yield, that makes them start, and then the wait says block until they're done.
yeah, so yield makes them start, and then co-await blocks until they're completed.
Yep.
Right. So that's I have to yield specifically a dependency object, but that's a template on any type of query. So
Yep.
there's a template class for any type of query. So
Yeah, okay. Because
yeah.
I can't parse through your templates fast enough to matter, seeing that they exist. And your actual queries, when you join them, you're doing an add. Is that a because that's the nature of the range of sums, you summing the left half
Yeah.
and the right half.
Right. So the output of a sum query is a uint64.
Yeah.
So when I await them, I get a uint64, another uint64, and then I add them.
Right. So this is a split two-way. Do you have an in-way split? Like
It divides by two at every step.
okay. So it's a fork join. So somewhere he has a decision that says either fork it or do the math locally.
Right. Right. So here's the local kind of where A is
Oh,
equal
you
to
fork
B.
down to one element. A equals B. You fork down to one element.
Yes, in this example.
Okay.
So this
Fine.
would probably be something where you could say, okay, if it's smaller than this, the scheduler probably it's probably not worth scheduling because there's more
Yeah.
scheduling overhead.
Yeah.
But I was really creating this to kind of benchmark the scheduler, so I didn't want to do that. But like if this was
Yeah.
a real
Okay.
implementation, I would say, okay, if there's less than, I don't know,
Right.
64 elements, do
Almost
this.
surely that number must be a lot bigger than 64.
No, it should be quite small actually because of the way the scheduler works. So like
Yeah.
I'll actually I can show you that. That might be interesting.
So, like
Um,
pick a range of sizes of arrays or something and then walk through the different sizes for the lower bound and see where you kind of hit your break even point. I'd be curious. Kind of depends on what your overheads are.
so like one of the reasons why this is probably like relatively low overhead is there's this
No, no,
like
no, 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 no. You never
exec.
play guessing games with this should be low overhead. Never. You just profile.
Okay,
It's the only thing you
right. That's true, but I still have more optimizations to do. But like this executor is like
it,
there's one
uh,
one
it's not that's not it's not I have more to do. You always have more to do. It's you profile it so you see where you're at and you can discover what is actually the next thing that needs to happen here, as opposed to I think this is important, and later you discover it was never important all along, but you just had no idea because something else was way more important. I'm
right.
just
Well,
saying you're at a point.
I can
Wow.
tell you from experience that if I lock and unlock a mutex and it's not another and no other threads are like if there's only one thread that's trying to grab a mutex, that's actually quite fast. So like there is this like the executor like it knows which thread it's executing on through this exec property. And so when we like get this like this is all like basically mutex free up until we um we
No, you're not
do
going to
this
convince me.
declare.
So I've played this game at many levels, at many times, many years, over and over and over again. The in use and practical placements where you have a large project, large application running along, they're always essentially impossible to figure out what the fuck was the real bottleneck until you started profiling. And then you could have some clue, but all that sort of academic, I put it together because in theory it looks really great. Always had these enormous bottlenecks in weird places, not even weird places, because that people were got a good academic start. That's nice, but
Yeah.
you profile and discovered this is the actual bottleneck, and now it
Oh
changes
yeah.
how we
Yeah,
measure.
I've done some profiling. That's why I got a 50 times speed
Yeah.
up. So if
I,
I run this
I ran a company
profile,
doing this kind of stuff, except we did it for way more complicated math and a lot bigger data sets. And like I said, the bottlenecks were rarely where you first thought they were. They eventually became where they thought they were, and you understood the problem very well. But they rarely started that way.
yeah, it's not 100% free, but like it's relatively low overhead compared to what the naive implementation was. So I can have this sort of
Well, I mean,
graphy.
the real naive implementation is I'm doing this range sum, right? I'm doing this sum over elements. The naive implementation is fry equals 0 to n, right? And that's x86 single core is optimized for. So you have to beat that. And spawning a second or a fourth or an eighth threads running in parallel, you'll run out of bandwidth at some point. You also have numerical instability. You want to do a bunch of other things you want to do here for numerical stability that are unrelated. Um, yeah, I claim go profile, see what you get. I'd be surprised
Just
if you got it right in one. You might get it
yeah,
right
it's
in
it's
one,
it's
but I
not it's not it's not optimized yet, but and like obviously yes, that is too small, but like
no. Don't obviously me. Run it, find out. I don't know what the right answer is. For the range sum, I'm suspicious. Like your 100,000, if that's the size of one of your arrays, I would claim that you probably are hard pressed to beat it with two threads. You maybe can. Depends on I don't know the modern costs. The costs that I was observing for launching a thread would far exceed would it take one core to go through 100 grand. Now, if the thread was up and running and you were doing a fork join task where you had a hot spinning waiting core waiting to jump on a CAS that unlocked and said go, the cost comes way down, maybe to 1,000 or something. But somewhere between 100,000 and 1,000, you start to hit this, I want to say this gradual flattening curve of where it mattered which way you went. But no one really cared for numbers that were 100,000 or less. It was too small. So we wanted bigger numbers, or we wanted 100,000 of 100,000s or something like that. Something big enough that it took a long time. And then it started to change where you wanted to do the splits and how you did them. So something to do, go profile. You're doing a performance hack, go profile it. It's a performance hack.
yeah. Yeah. So this is
I'm trying to
the
get my functionality going, and then I'll go performance hack on simple.
so this is like I'll time it real quick. So I have the time. Yeah, so here's with the concurrent map. So that was zero point
Yeah,
0.5 seconds.
yeah, okay.
And then I'll turn the concurrent map off.
And this is now using a single lock on with multiple cores.
Yeah, so I have this property in the settings. I'll change that setting real quick. Um, and then I'll run it again. Well, let me click build first. So I'll build it with the concurrent map off and then run it again.
Right. And you're going to get some giant change up. Now, the other piece that wants to happen here. So according to this user mode time, you got twice as fast. Oh, okay, nice. Now, the another one is to use an unsynchronized map and one core. Be correct, but only use one core. But get rid of all bogus synchronizations everywhere because you don't need them in your one core. Beat the one core. And
Okay.
and maybe you do. And look at how much work's going on. Like your ranges from 100,000 to 400,000, whatever, those the cost to launch a thread should be almost on par with summing, 100,000, which is going to be whatever, 10,000 cache lines or less. uh,
Okay.
streaming pipeline through an x86, that's going to be in the low microsecond range, which is thread launch time.
Okay, so I'll do it with just one
Yeah, you
thread
have to
here.
turn off all locking though as well, because that's like bogus overhead right now.
Okay.
There you go.
Made it half.
Yeah,
Cut its speed in
I'm
half.
claiming
This is
wall
actually
clock
not a good. This is
wall
this
clock
one.
time was twice as fast as two cores with good threading.
Yeah, but this one is
Yeah, you
this
just
one, the Fibonacci actually parallelizes a lot more. The range sum didn't go very well. So let me do 35 here.
so you have to run them with your other. Yeah, so now you're tuning your results to make one look better than the other.
Well, yes, I'm looking at the CPU also. It didn't really thread. So like this one, okay, that's
I thought we
the
were doing one thread. You shouldn't be. You should have CPU should be.
yeah, but in the other case it also didn't. So okay, so this is 3.42432, right?
I'm looking at
So
the wall clock time, but okay.
okay,
And now go back to multi-threaded and good hash table.
okay.
Like the
So
multi-threaded with the bad hash table is like a no-brainer loser. Like you gotta fix that.
okay, and then I'll just set this to let's leave it at two, maybe, or just one.
Well, I don't know what hardware concurrency means.
It's number of threads on the computer. Okay, so I run again.
To be equal to the number of threads, not double, unless you have
Wait,
something
what?
else. You
What
didn't
did I
didn't
do?
really win there.
What did I do? Am I using the wrong one?
So
Uh,
another thing I've
it's
discovered is
off.
that
Yeah, it's off.
when I do profiling, I'm doing like this, where I'm hacking and changing and test. I frequently make a lot of mistakes. I make a lot of mistakes. It happens all the time, and I need to get to a self where I have a
Okay.
reliable setup that I can A/B test. And I usually discover after I've made some cool hack to make something go better that I've busted my testing. I failed my original testing, and I wasn't testing the correct thing in the first place. And so all my prior numbers were crap because I was testing the wrong thing.
All right,
That
so
happens a
this
lot.
is with the concurrent. I had the concurrent map off. This is with the concurrent map on. Okay, 1.6,
Right. And you raised
and
you to make this work, you raised Fibonacci, which is an intended to be a fork join like thing.
yeah, it's kind of that one's intended to be a mixture. Actually, it's more the first one that's more of the fork join. But
Not
it's
Fibonacci? Is it you're not just forking the left and the right sums?
no, the Fibonacci does one fork at the like it calculates the other half like entirely single threaded kind of. So it's like each one of them's relatively heavy.
Okay. Okay.
Um,
That would be,
okay, so
relatively heavy is a good term for when it's time to, the right amount for having two threads.
yeah, so it's at least twice as fast in this situation. I don't have a good a good workload
Now, I
though.
was looking at range sum because I know that it's x86 is ideally suited for walking an array and summing the elements. That's sort of a sweet x86 thing. In which case, the cost of it is lower. So the length of the array that you need to have before it's worth it to have two cores running is bigger. And then because any one core in x86 typically can eat most of the bandwidth, by the time you get to like four cores, you hit diminishing returns because you're out of bandwidth. You got CPU clock cycles aplenty. You just got no bandwidth.
Yeah,
I don't know what you're doing here. All right, I'm gonna
I'm
be
just
done because you're flipping things rapidly and we don't know what we're doing here. So it's
yeah. I was just trying to get it to like
yeah,
use more threads, but it's not.
right.
The release mode is too fast.
Okay. Things to go do at some future date for sure.
Yeah, I need
Um,
to find a I
I,
need to
I,
find a better problem to like test out the
yeah,
extender because
right.
like
Yeah,
this
exactly.
these are not like
Yeah,
fully
right.
utilizing the CPU. Like it finishes
Yeah, 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 yeah.
before.
Back in the day, starting at H2O, we were a solution in search of a problem. We did a lot of linear regressions, which was basically multiply some adds and then some nice math afterwards. And we did some amount of k-means. K-means is a good one to try to experiment with parallelism on. Um, but getting big problems to play these games with was took a while. We had to like talk to clients and customers And then eventually they started opening up and handing us data sets. And then these would be enormous problems. And we were like, oops, look at this. We had got to go deal with handling a billion things instead of, an array of a million ints that I randomly generated. That only goes so far. An array of a million strings I'm putting in my hash table to test its concurrency. That only goes so far. You get a real client, you get all kinds of wild shit going on that needs, and then you discover your bottlenecks. All right. Um, well, thank you for showing today at short notice. And thank you for the certainly APO's discussion on, I want to think about uh, 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 how lifetimes and different memory spaces for the GPU versus not the GPU fit into my thinking on what I do with types, which maybe they don't fit, and I need to rethink that solution all ways around. But I have a day's worth of things to go fix around my house, so I'm out of here. Next Friday, I'm hoping, no panic mode, no short notice doctor's appointments, no lot of things. Should be next Friday just fine. All right, bye bye.
Right.